Hi children, welcome to another chemistry class. In this session, we are discussing aldehydes, ketones, carboxylic acids. Second year topic, aldehydes, ketones, carboxylic acid. One of the important organic chapter from the 12th standard syllabus, right? Let's have a look at a review on the important points concerned to the chapter. Aldehydes, ketones, carboxylic acid. All of you know aldehydes carry a functional group CHO. This is the functional group carried by aldehydes. And the ketones, this is the functional group ketones. And carboxylic acids, this is the functional group carboxylic acid. Known to all, right? So aldehyde functional group is otherwise called a formyl group. It is CHO group. Ketone, it will be CO functional group, and carboxylic acid will be COOH. All of you know that. So aldehydes will be represented as RCHO, and simplest aldehyde is HCHO, formaldehyde, methanol. That is the simplest aldehyde, formaldehyde. The next member is acetaldehyde, CH3CHO, ethanol, acetaldehyde, ethanol. So this is the functional group that repeatedly coming in: methanol, ethanol, propanol, butanol, and aromatic aldehyde, benzaldehyde. Aromatic aldehyde, benzaldehyde, called benzene carbaldehyde. Benzaldehyde. It is actually benzene carbaldehyde, which you get a privilege of calling as benzaldehyde, right? Oil of bitter almonds. So that is about aldehyde and their structural entity. Aldehyde structural entity will be like this: C double bond OH. This is the structural entity of aldehydes. That is also known to all, where carbon undergo sp2 hybridization and trigonal planar system. Trigonal planar system. While ketones, once again, it is sp2 carbon, and it is trigonal planar system, sp2 carbon, trigonal planar system. And the simplest ketone is known to all, acetone, propanone. This is the simplest ketone, the so-called acetone. IUPAC name, propanone. That is the simplest ketone. Acetone, propanone, butanone, pentanone, hexanone, like that. And aromatic ketone, simplest aromatic ketone, acetophenone. Simplest aromatic ketone, acetophenone. Acetophenone is the popular IUPAC, common name which is accepted by the IUPAC also, or it may be called as 1,2,1-phenyl ethanone, like that. That is aromatic ketone. Now the point is, aldehyde and ketones, they are together called as carbonyl compounds because of this group. This group is called a carbonyl group, and they are called carbonyl compounds. And in that sense, they have many similarity in their activities. They are referred as carbonyl compounds and dealt together in many studies. Aldehydes and ketones are dealt together in many studies because of its carbonyl nature. Okay. While coming to carboxylic acid, it is COOH. The structural entity will be COOH, like this. Once again, this is sp2 carbon and is called a carboxylic acid. There is a carbonyl group and there is a hydroxyl group, together called a carbonyl hydroxyl, called a carboxyl. carboxyl group. It is called a carboxylic acid. Carboxylic acid, that is the structural entity of carboxylic acid. Even though there is a carbonyl group, it is not called as carbonyl compound because it is acid. It is having properties of acid. That is the reason. And the simplest carboxylic acid, it is formic acid, HCOOH, formic acid, that is methanoic acid, methanoic acid, formic acid, right? The next one is acetic acid, CH3COOH, acetic acid, ethanoic acid, ethanoic acid, acetic acid, ethanoic acid, acetic acid, like that. And then there is benzoic acid, aromatic acid, benzoic acid. It is benzene carboxylic acid, get the privilege of calling as benzoic acid. Benzoic acid, benzene carboxylic acid, benzoic acid. These are the important class of compounds that come to the heading discussion: aldehydes, ketones, carboxylic acids. And I am sure all of you remember there are derivatives of carboxylic acid. What are the derivatives of carboxylic acid? There are certain important derivatives. This is carboxylic acid, RCOOH. Imagine this OH replaced by chlorine. You get RCOCl, called acid chloride. Acid chloride or acyl chloride, right? That is number one. And this OH replaced by amino group, you get RCONH2, that is acid amide, acid amide, right? And then OH group replaced by alkoxy group, you get RCOR dash, RCOOR dash, esters, 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 RCOOR dash, esters. And then acid anhydrides, RCOOCOR, acid anhydrides. These are various derivatives of carboxylic acid: acid chlorides, acid anhydrides, esters, amides, right? So these are dealt in the chapter. Mainly we are concentrating on aldehydes, ketones, and then carboxylic acid, and few discussion about derivatives of carboxylic acid, also acid chlorides, acid anhydrides, esters, amides, right? These are the structural details of those systems. Fine. That is what dealt in the introduction portion, and there are few important compounds also dealt, like vanillin, like this is vanillin, and there is a talk on salicylaldehyde, salicylaldehyde, vanillin, salicylaldehyde, cinnamaldehyde. What is the IUPAC name? Vanillin, vanillin, IUPAC name. Simple, no? It is 1, 2, 3, 4. It is 4-hydroxy, 4-hydroxy, 3-methoxy, 3-methoxy, benzaldehyde. Benzaldehyde, that is the popular one. Vanillin, vanillin obtained from vanilla beans. Salicylaldehyde, very simple, 1,2-2-hydroxy benzaldehyde, 2-hydroxy benzaldehyde. And what about this one? It is 1, 2, 3, 3-phenyl propanol, 3-phenyl propanol, 1, 2, 3, 3-phenyl propanol, cinnamaldehyde, cinnamaldehyde. So such molecules are represented in the systems and in the textbook. We need to review the characteristics of such molecule, not only naming the features also. Question can be of any kind. Now coming further, the naming part, simple molecules, acetaldehyde, benzaldehyde, common name beta bromo butyraldehyde. This is the functional group. Knowing alpha beta carbon is very important. This is functional group. Functional group connected carbon is called the alpha carbon. The next carbon is called the beta carbon. The next carbon is called the gamma carbon. The next carbon is called the delta alpha, beta, gamma, delta, so on. And here it is beta bromo butyraldehyde. What is IUPAC name? 1, 2, 3, 4. 3 bromo butanol. 3 bromo butanol. That is the name. Okay, fine. Look at the next molecules, acetone, propanone, acetophenone, 1, 2, 1-phenylethanone, propiophenone. What is the IUPAC name? Propiophenone. This is common name. 1, 2, 3, 1-phenyl, 1-phenyl propan 1 on. 1-phenyl propan 1 on. 1-phenyl propan 1 on. 1-phenyl propan 1 on. That you need to give 1 on because there is 2 on. 1-phenyl propan 2 on. It can be like this, no? CH2 CO CH3. So it is 1-phenyl propan 1, 2, 3. 1-phenyl propan 2 on. It can be 1-phenyl propan 2 on. It can be. While that is benzophenone. Look at the naming part again here. Ethanol, acetaldehyde. 1, 2, 3, 4, 5, 6, 7. So it's going to be 4 bromo, alphabetical order. 4 bromo, 3 methyl heptanol. What about here? It is 1, 2, 3. 3 methyl cyclopentanone. 3 methyl cyclopentanone. Look at this molecule. Look at this molecule. It's called cyclohexane carbaldehyde. Cyclohexane carbaldehyde. While a similar system, if it is aromatic, benzene, we give the privilege. It may be called as benzene carbaldehyde. We give the privilege benzaldehyde. That cannot be done here. Okay. Pent-2-enol, 1, 2, 3, 4, 5. Pent-2-enol, pent-2-enol, pent-2-enol. What about here? It's already we have discussed 1, 2, 3. 1-phenyl propan 1 on. You need to give 1 on because this keto group can be over here also. See that 1-phenyl propan 2 on it can be. So there are 2 compounds. You have to give the name 1 on, 2 on like that. Okay. What about here? What about here? There are 2 functional groups. There is a functional group here and functional group here. So this is the principal functional group, known to all. So it is 1, 2, 3, 4, 5. So it is 3-oxopentanol. 3-oxopentanol. What is here? 1, 2, 3, 4, 5. It is 2,4-dimethyl. 2,4-dimethyl pentan 3 on. 2,4-dimethyl pentan 3 on. What is here? 1, 2, 3, 4. 4-nitrobenzaldehyde or benzene carbaldehyde. 4-nitrobenzene carbaldehyde or benzaldehyde. Here we have something special. In such a molecule, we need to take this as the parent chain. So it will be 1, 2, 3. Propane 1, 2, 3 tricarbaldehyde. Propane 1, 2, 3 tricarbaldehyde. So when a functional group repeat more than twice in a chain, when a functional group repeat more than twice in a chain, 1, 2, 3, you have to take the parent chain like that. Propane 1, 2, 3 tricarbaldehyde. Okay. And there are more examples in the table also. All are known examples only. So you may try practicing all these. Just have a look at acrolein, propanol, prop-2-enol. Not necessarily you give prop-2-enol. There is only prop-2-enol, only one compound. So it is propanol, simply propanol, acrolein. This is thaldehyde. You know thalic acid. Thalic acid is COOH. This is thaldehyde. Benzene 1,2-dicarbonaldehyde. The complementary compound related to thalic acid. Mesytyl oxide. Look at mesytyl oxide. CH3 twice. C double bond CH. COCH3. This is mesytyl oxide. What is the IUPAC name? 1, 2, 3, 4, 5. It is 4-methyl. Pent 3-ene 2-on. It is in fact obtained by the condensation of two molecules of acetone linearly. When two molecules of acetone linearly condense, we get mesytyl oxide. Right? There is another molecule when three molecules of acetone condense linearly. When three molecules of acetone condense linearly, you get CH3, CH3 double bond CH, COCH. A similar system repeat here. That is three molecules of acetone condensing. This is one acetone, two acetone, third acetone. And look at the molecule. It's a symmetric molecule which can be numbered from either side. 1, 2, 3, 4, 5, 6, 7. So it is 2,6-dimethyl. 2,6-dimethyl. Hepta, 2,5-diene, 4-on. That is the name. 2,6-dimethyl hepta 2,5-diene 4-on. That is the molecule. A very famous molecule also called 4-on. It is called 4-on. Maybe because of that last part of the naming, 4-on. So practicing this is very important from the initial segment of the chapter, naming part. Coming to the structural details of carbonyl compound. This is what the structural details of carbonyl compound. The carbon undergo sp2 hybridization. The carbon here undergo sp2 hybridization and a trigonal planar system with a bond angle 120 degree on an average. So carbon makes a 3 sigma bond sp2, sp2, sp2. 3 sigma bond, one here and one with oxygen. And there is a pi bond between the p orbital of carbon and p orbital of oxygen. It makes a lateral overlapping like this, making a pi bond. And this is the pi bond electron cloud shown above and below by the overlapping of these two lobes and these two lobes. That is a one pi bond. You must try to assume why this pi electron cloud is given in that shape. Why that pi electron cloud is given in that particular shape? Simple logic. It is so simple that the electron cloud is more drifting towards oxygen. You know, oxygen is more electronegative. Oxygen being more electronegative, the pi electron cloud is more shifting. Normally the electron cloud shifting more towards oxygen, as oxygen is more electronegative in nature. That is the nature of carbonyl compound. Carbonyl compound is highly polar. Carbonyl system is highly polar. Why carbonyl system is highly polar will be demonstrated by this character. You see this? This is the carbonyl system, and try to understand why it is highly polar. It is polarizing as minus and plus. So there is in carbonyl system, you have this permanent polarization. There is a permanent polarization. Carbon, oxygen, it is coming. Oxygen, highly electronegative system connected to carbon causes the high dipole moment created by the carbonyl compounds, just like nitro compounds, etc. So that is another important point. And here you have one electrophilic center and one nucleophilic center. This will be acting as a electrophilic center. Meanwhile, the other one will act as a nucleophilic center. This will act as a nucleophilic center. O minus act as a nucleophilic center and C plus act as a electrophilic center. Which is more reactive? Is it C plus electrophilic center or O minus nucleophilic center? Which is more reactive? No doubt it is C plus electrophilic center, because it is not having octet. It is an electron deficit center and hence it is more reactive, while oxygen is happy to be there like having octet. It is having 8 electrons. It is happy there and comfortable. So that is about the structural details of carbonyl system. Structural details of carbonyl system and the naming, etc. Now on to preparations of aldehydes and ketones. Preparation of aldehydes and ketones. First method already learned one, oxidation of alcohols. All of you know primary alcohol, upon oxidation you get a aldehyde, which need to be done controlled manner. Otherwise aldehyde will be further oxidized to carboxylic acid. All of you know. And secondary alcohol will give you ketones. So that is the reaction. Primary alcohols are CH2OH. Upon oxidation, this one hydrogen and one of this hydrogen out, and you get RCHO, aldehydes. So primary alcohol will give you aldehydes, and the reaction is easy and comfortable reaction. And further it may be oxidized to carboxylic acid. And if you want to stop here, you have to make a controlled reaction. Already we have learnt in the previous chapter, either by using PCC, pyridinium chlorochromate, or by using anhydrous CrO3. We can do that, right? So that is the point. Primary alcohol, upon oxidation, easy oxidation to get aldehyde. While if you take a secondary alcohol, it is not so easy, but still under elevated condition you can conduct the oxidation. These two hydrogen will be out and you get a ketone. So primary alcohol you get a aldehyde, and secondary alcohol you get a ketone. So that is number 1, right? Number two, dehydrogenation. Dehydrogenation, once again it is oxidation type reaction using heated catalyst. Heated copper and silver, dehydrogenation process, that also learned in the previous chapter. Alcohol vapors passed over heated copper catalyst or silver catalyst. If you take primary alcohol RCH2OH, when passed through heated copper catalyst 573 Kelvin, there is dehydrogenation, H2 out. H2 out, and you get aldehydes. So primary alcohol will give you aldehyde, secondary alcohol will give you ketones. The same procedure. There is dehydrogenation reaction. It is in fact an oxidation type reaction only, right? What about tertiary alcohol? So primary alcohol, dehydrogenation, you get aldehyde. Secondary alcohol, dehydrogenation, you get ketones. What about tertiary alcohol? Do you remember? Tertiary alcohol undergo dehydration. You get a alkene. If you take a tertiary alcohol, if it is secondary alcohol, there is dehydrogenation. You will get a ketone. There is dehydrogenation process, removal of H2. While if you take a tertiary alcohol, this is tertiary butyl alcohol. When heated with a copper catalyst, this OH and one hydrogen out, and you get dehydration process to get a alkene. It is not removal of hydrogen, it is removal of water. It is dehydration process. Already learnt. So that is reaction number 1, oxidation of alcohol, quite similar one, dehydrogenation of alcohols. And then from hydrocarbons, again a reaction learned in the 11th standard topic, ozonolysis of alkenes. Ozonolysis of alkenes, very popular reaction. Ozonolysis reaction. Ozonolysis reaction. Ozonolysis reaction with ozone followed by reduction cleavage, zinc and water. All of you know it is a test for unsaturation. It is a test for the type of unsaturation. It is a test for finding the number of unsaturation. It is a test for finding the position of the unsaturation. Ozonolysis is very important. It helps us to understand whether there is double bond or triple bond. It helps us to understand whether it is double bond or triple bond. It helps us to understand how many double bond are there. It helps us to understand where the double bond is. By looking at the nature of the product, we are able to predict all these categories, characteristics. Right? The simplest reaction we know, it is ethene added with ozone. Ozone added across the double bond using 2 bonds. You get ethene ozonite. This is ethene ozonite. Ethene ozonite. And that ethene ozonite, when treated with zinc and water, it is called reduction cleavage. There is oxidative cleavage that also maybe you are aware of. Using H2O2, there will be oxidative cleavage giving acids and all. It is going to be a cleavage like this. This oxygen carried away by zinc, zinc oxide out, and you get 2 molecules of HCHO. CH2O, that is HCHO. You get 2 mole HCHO like that. And all of us know how to predict the product directly from the molecule. It is just matter of breaking over the double bond and attach one oxygen like this to predict your product. You get 2 moles of formaldehyde like that. Right? So wherever you find a double bond, you can break it and attach one oxygen to understand which will be the product. Right? Say for example, if you are given with such a alkene, what will be the ozonolysis product? What will be the ozonolysis product? Yes, it will be a cleavage over here, a oxygen here, that is CH3, CO, CH3, you get acetone. And now here there is an oxygen, it is going to break here, here there is an oxygen, this is CHO called glyoxal. And this is formaldehyde. Here one oxygen, formaldehyde. You get HCHO, formaldehyde. So you get 1 mole formaldehyde, 1 mole CHO, glyoxal, and 1 mole acetone. So if you are getting 1 mole acetone, 1 mole glyoxal, 1 mole formaldehyde, it could be this alkene. You have to think of the reverse also. When the product is given, when a product combination is given, what could be the reactant molecule? You should be able to predict. Right? So practicing more on this content is very important. There are different kind of alkenes or alkynes. When given, what will be the ozonolysis product? And if different ozonolysis products are given, what could be the reactant alkene? You must try to practice, including cyclic systems. Say for example, suppose it is so given, methyl cyclohexene, for example. Methyl cyclohexene, when treated with ozonolysis, treated first with ozone, followed by zinc and water, what will be the product formed? See, we can easily predict, we can easily predict it's going to cleave over here. Here one oxygen, here one oxygen. So what is going to be the product? What will be the product formed? You see this, there is a CHO here and you get a CO here. This is the product. It is going to cleave here. This carbon will turn CHO and this carbon, there is no hydrogen, you get a CO. And what is the name of the molecule? What is the name of the molecule? 1, 2, 3, 4, 5, 6, 7. It is 6-oxoheptanol. 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 That is the product formed. Isn't it? So similarly, practicing more on this content, different kind of cyclic and open chain molecules of alkenes and alkynes taken for identifying the ozonolysis product, very important competitively as well as the board exam point of view. While the next one reaction number 1, oxidation of alcohol, reaction number 2, dehydrogenation of alcohol, reaction number 3, ozonolysis, and now it is hydration of alkynes. Hydration of alkynes. Alkynes undergoing hydration. What is the procedure involved? That also learned in the 11th standard topic, hydration of alkyne. If you take ethyne, for example, when treated with water in acid medium along with the mercuric salt. What is the purpose of mercuric salt? We don't use mercuric salt during the hydration of alkene. Alkene is simply acid catalyzed hydration. What is the purpose of mercuric salt in alkynes? Alkynes has got a cylindrical electron symmetry and we need to give extra triggering for the polarization of alkynes, triple bond. That is the purpose we are using mercury. So what will be the nature? It is hydrogen added here and OH added here. You get CH turn CH2, triple bond turn double bond, and you get CHOH. This is called enol, vinyl alcohol. Vinyl alcohol. And this vinyl alcohol undergo an isomerization change. What is that isomerization called? Exactly, tautomerism. It undergo tautomerization. Tautomerization. This hydrogen migrating here and this double bond comes between carbon and oxygen. You get CH2 turn CH3, double bond turn single bond, and you get CHO, that is ethanol. So if you start with the ethyne, you get ethanol. Ethyne upon hydration, you get ethanol. While higher alkynes, you get ketones. Right? Higher alkynes, you get ketones. That also we have learned. Suppose we are dealing with a higher alkyne, say propine or any higher alkyne. It is treated with water under similar conditions, H plus and mercuric salt. I don't have to tell you H plus and OH minus. OH minus will be coming to this carbon, isn't it? Marconic of addition. So hydrogen is added here, OH minus is added there. You get CH3, COH, triple bond turn double bond, CH2. Again, you get an enol. And that enol undergo, what is the process? Tautomerization. This hydrogen will be migrating here and this double bond will be shifted to carbon oxygen. You get a ketone, CH3, CO, CH3. You get a acetone. So this is what the scenario regarding the hydration of alkynes. If you take the first alkyne, ethyne, you get ethanol. Higher alkynes, you get ketones. Any higher alkyne, you will get a ketone. Right? Suppose you are dealing with such a alkyne given to you. You can think about, you may get two different, suppose you are dealing with such an alkyne. Suppose you are dealing with such an alkane undergoing hydration, which will be the major product of ketone formed. What will be the different ketones that you may get and which one will be the major product? You can think of your own. this kind of an alkyne given to you undergoing hydration, what are the ketones that probably you may get? Of which one will be the major product? You can think and find out. Okay. So that is about ozonolysis reaction, that is about hydration of alkyne, that is about oxidation of alcohol, that is about dehydrogenation of alcohol using copper catalyst. Now comes the very popular, very famous reaction, preparation of aldehyde from acid chlorides. Preparation of aldehyde from acid chlorides. Very, very popular reaction, the so-called Rosenmund reduction. Rosenmund reduction. Acid chloride treated with hydrogen with the palladium barium sulfate. Palladium added with the barium sulfate. Added with a slight bit of sulfur or quinoline or calcium carbonate or carbon. The catalytic activity of palladium controlled. Active centers of palladium controlled by packing with the barium sulfate, with the charcoal, with the poisoned with the sulfur or quinoline. All of you know it is called a Lindlar's catalyst. This is called a Lindlar's catalyst. And what is the purpose of Lindlar's catalyst? It just suppresses the catalytic activity of palladium so that an acid chloride we are taking, for example, benzoyl chloride we are taking, the chlorine replaced by hydrogen, you get benzaldehyde. Sir, what happens if we don't take the controlled reduction? This is controlled reduction. Lindlar's catalyst is providing controlled reduction. How we control? We take palladium with hydrogen. Number one, we take limited amount of hydrogen. Number one. Number two, we take palladium packed with the barium sulfate or packed with the charcoal or packed with the calcium carbonate, added with a slight bit of poisoning component like sulfur or quinoline. What is the purpose of doing that? We are about to control the catalytic effect of palladium. Otherwise, what will happen? Acid will be reduced to aldehyde. Aldehyde will be reduced to alcohol. Benzoyl chloride reduced to benzaldehyde, reduced to benzyl alcohol, which we don't want to happen. And that is the speciality of Rosenmund reduction. This is called a Rosenmund reduction, preparation of aldehyde. Acid chloride treated with the Lindlar's catalyst, that chlorine replaced by hydrogen, you get aldehyde. Benzoyl chloride converted to benzaldehyde. The very popular one, Rosenmund reduction. Rosenmund reduction. What is the speciality of the catalyst? Lindlar's catalyst is used. What is Lindlar's catalyst? The catalytic activity of palladium controlled, suppressed by adding certain components. Right? Next reaction from nitriles and esters. From nitriles and esters. Have a look at another popular reaction. Nitrile, the so-called cyanide, reduced to aldehyde. The reaction called Stephen reduction. Stephen reduction. Nitriles reduced to aldehyde. How do we do? Treated with stannous chloride HCl. Stannous chloride HCl can give stannic chloride SnCl4 producing H, and this is providing the reduction procedure, and this H will be added across CN triple bond. Across CN triple bond, this hydrogen will be added and you get aldehyde. This is aldehyde. You get imine. Is it complete reduction or partial reduction? Is it complete reduction or partial reduction? No doubt, partial reduction, because triple bond is reduced to double bond. One H2 is added. What is the complete reduction product? Suppose it is completely reduced. The product will be RC. C becomes CH2. N becomes NH2. You get a primary amine. That is a complete reduction procedure. This is not complete reduction. This is partial reduction. And what do you get? You get aldehyde. And that upon hydrolysis, this part of the molecule will turn aldehyde. Aldehyde. Upon hydrolysis, you get aldehyde. That is called a Stephen's reduction. Stephen's reduction. So, Rosenmund reduction, Stephen's reduction. Rosenmund reduction, acid chloride converted to aldehyde. Stephen reduction, nitriles converted to aldehyde. Nitriles first converted to aldehyde. Nitriles first converted to aldehyde, and from there it is converted to aldehydes. Okay. While there is another alternative technique using dibal H. What is dibal H? Diisobutyl aluminum hydride. Diisobutyl aluminum hydride. What is diisobutyl aluminum hydride? This is dibal H. Diisobutyl aluminum hydride. This is aluminum, and this is diisobutyl. This group is called the isobutyl group. This group is called the isobutyl group. This is diisobutyl aluminum hydride. Diisobutyl aluminum hydride. One hydrogen. This is isobutyl aluminum. This is isobutyl group. Diisobutyl aluminum hydride. Dibal H. Dibal H also giving a controlled reduction reaction, and you see the procedure happening. Again, nitrile is reduced to aldehyde. Nitrile will be reduced to aldehyde first. Nitrile will be reduced to aldehyde first. This will turn RCH double bond NH. From there it is converted to aldehyde. And dibal H has got another speciality also. Suppose you take such a system where there is an unsaturation. You can see it is giving a selective reaction. CN reduced to CHO, and the unsaturation remain intact. Unsaturation get undisturbed. It is a selective reduction procedure. It doesn't affect the unsaturation across the chain, remaining chain available. It is a selective reduction. So, reaction number 1, reduction of alcohol, hydrogenation of alcohol, ozonolysis, hydration of alkyne, Rosenmund reduction, Stephen reduction, now using dibal H. Dibal H may also help us to reduce to acids and derivatives, esters. Esters can be reduced to aldehydes. This is an ester which is reduced to this part of the ester reduced to aldehyde. Dibal H can reduce esters, not only esters, acids and derivatives, acids, acid chlorides, esters can be reduced to aldehyde by using dibal H. Only ester is given in the text. Right? Next is from hydrocarbons. Hydrocarbons. Preparation from hydrocarbons, particularly aromatic aldehydes, benzaldehyde and derivatives prepared from side chain oxidation. That is the next process. So how a compound like say toluene can be oxidized to benzaldehyde, that is our discussion. Normally, you know, when toluene is oxidized, you will get benzaldehyde, and that will be further oxidized to benzoic acid. That is what happening. So if you take say toluene, there will be side chain oxidation. If it is treated with a strong oxidizing agent like KMnO4, there will be oxidation, and this carbon will be turning. First may turn aldehyde, and then subsequently it will be converted to carboxylic acid. So the final result is side chain oxidation. Final result is carboxylic acid. And you know that happens irrespective of the length of the chain, whether it is one carbon side chain, 2 carbon side chain, whether it is methyl group, ethyl group, propyl group, whatever it is, other than tertiary butyl group, irrespective of the length of the side chain, you will get benzoic acid. That is what happening. Here, you know, we want benzaldehyde. So we do some special type of procedure. First of all, oxidation of methyl benzene, that is done specifically using a reagent CrO2Cl2 using chromyl chloride. Using chromyl chloride, we conduct the reaction. This is what chromyl chloride, all of you know. This is what chromyl chloride, CrO2Cl2. Using this, a special type of reaction we conduct on the oxidation part of the side chain part of the benzene molecule, that is toluene or such systems. And is very popular reaction known to all, maybe Etard's reaction. We are going to discuss Etard's reaction using chromyl chloride, side chain oxidation of benzene using chromyl chloride. You see toluene interacting with the CrO2Cl2, you get a chromium complex like this. This CrO2Cl2 is added over here. How it is added? Please have a look at this particular area. It is CH. The two hydrogen atom is interacting or replaced by the interaction of chromium. The two hydrogen atom, it is O, Cr, O, Cl, and this becomes OH, Cl, like this. And one more, O, Cr, OH, chlorine, like this. We get such a chromium complex. You see that 3 out of the 3 hydrogen atom, 1 hydrogen is retained there, and the 2 hydrogen atom replaced by OCrOHCl2 twice. OCrOHCl2, 2 numbers like this, right? And now this upon hydrolysis, you can see this is a gem molecule type, and you see what's happening over this region upon hydrolysis. This will turn to OH group. That will turn to OH group. All of you know, one carbon cannot hold more than one OH group. Gem diol is unstable. Gem diol is unstable, or every such situation when hydrolysis happens, you can see if it is turning OH, it will eliminate water molecule and it will turn CHO. You see it gets like this. There is H. Imagine it's converting like this. Just imagine you will lose a molecule of water and it will turn CHO. You will get CHO like that. So toluene CH3 group, the 2 hydrogen atom replaced by the chromyl chloride that we are using, and it forms a addition type complex, and that complex enable COO linkage, CO linkage, and that finally upon hydrolysis you will get aldehyde. Suppose there is C coming with the 3O. Upon hydrolysis, you will get carboxylic acid. Here we are controlling that character. Hope you get it. So out of the 3 hydrogen, 1 hydrogen retained there, and the other 2 hydrogen atoms allowed to, and that region is allowed to oxidize, so that we can limit the reaction on the aldehyde stage. Otherwise, normally, what happens with the KMnO4, like a strong oxidizing agent, we get carboxylic acid. Okay. So that is the very popular reaction. All of you know it is Etard's reaction, right? So few minutes back we were talking about the Rosenmund reduction, Stephen's reduction using diol H. Now a special type of reaction, Etard's reaction. We can have a similar reaction. Toluene treated with acetic anhydride. Acetic anhydride and CrO3. Toluene treated with acetic anhydride and CrO3. CH3COOCOCH3. Acetic anhydride interacting over this region. What do you get is, you get a benzylidine diacetate. You know what is meant by lidine? Benzylidine means gem diacetate. You get a gem diacetate. Please see what is the character of that system. It is CH once again, as I said earlier. It is CH, then O, COCH3, OCOCH3. You get a benzylidine diacetate. And once again, the nature of the system is quite similar to what we have seen earlier. This 2O will be, upon hydrolyzing, it will be converted to, there is one hydrogen remaining. You will be getting CHO. You will be getting CHO, benzaldehyde. That's also happening similar to what we have explained in the previous case. There we are using chromyl chloride. Here it is interacting chromium oxide with the acetic anhydride. You get benzylidine diacetate. The name of this molecule is benzylidine diacetate. The name illidine, that means gem diacetate. Finally, it is converted to benzaldehyde. Okay. So that is Etard's reaction and a reaction using acetic anhydride. Next is side chain chlorination followed by hydrolysis. Side chain chlorination. In fact, side chain chlorination of toluene, you can have three characteristic reaction. Three characteristic reaction you can expect. One is what we are discussing over here. Suppose you take toluene. It is treated with chlorine. It is treated with the chlorine in presence of light. It is treated with the chlorine in presence of light. In fact, you know, primarily there can be three substitutions are possible. Number one of the hydrogen atom replaced by chlorine, where you get the so-called benzyl chloride. This is called benzyl chloride. And what will happen upon hydrolysis? This taken for hydrolysis, solvolysis, you get benzyl alcohol. That's it. You get benzyl alcohol. So one hydrogen replaced by chlorine, monochlorination. Monochlorination, if it take place, you get benzyl chloride, and that upon solvolysis, you get benzyl alcohol. Okay. Next is benzyl chloride. Benzyl chloride. Two hydrogen atom replaced by chlorine. This is called benzyl chloride. Benzyl chloride. Where two hydrogen atom replaced by chlorine. Imagine upon hydrolysis, what do you get? I don't have to tell you, the two chlorine atom upon hydrolysis, there will be two OH group comes, which is not possible because gem diols are unstable. Immediately one water molecule is out and the result will be benzaldehyde. You get benzaldehyde. So one substitution occurs, you get benzyl alcohol. Two hydrogen substituted by chlorine, you get benzaldehyde. What about if all the three chlorine hydrogen substituted by chlorine? No doubt all of you easily can know, and all of you know. It's very simple logic also. You get benzoic acid. You see what happens? All the three hydrogen atom replaced by chlorine. You have CCl3. Upon hydrolysis, what is the result? Upon hydrolysis, what is the result? This upon hydrolysis, you can assume it may be so happening. All the three chlorine atom replaced by OH group, which is not possible, and immediately it will eliminate one molecule of water and you get benzoic acid. Benzoic acid. You get like this, benzoic acid. So out of toluene CH3 group, one hydrogen atom monochlorination happens. You get a benzyl chloride, solvolysis, benzyl alcohol. Two hydrogen atoms substituted, disubstitution, dichloro substitution, you get benzyl chloride, you get a benzaldehyde. Three hydrogen substituted, trichloro, benzo trichloride, you get a benzoic acid. Of which this is our point of discussion in the chapter as we are talking about aldehydes. This is our point of discussion in the chapter. There are two substitutions happening and the final result will be benzaldehyde. In fact, we should know all the three cases. Is it clear? Is it clear? So, Etard reaction, reaction with acetic anhydride involving CrO3, side chain chlorination. Side chain chlorination, in fact, there are 3 cases. Second case is the point of discussion as we are in the current particular chapter. Okay. Of course, this is also important. Fine. And what about next? Next is a very popular reaction, Gatterman-Koch reaction. Gatterman-Koch reaction. That is the next one. Gatterman-Koch reaction. What is that reaction? Benzene treated with COHCl and anhydrous AlCl3. So, carbon monoxide with HCl treated with benzene in presence of a Lewis acid. I think many of you are aware of what happens with the carbon monoxide and HCl will be, you will be getting HCOCl, formyl chloride. Formyl chloride is unstable and is prepared in situ by mixing CO and HCl. Now, this bond is breaking and is out as Cl minus, and you will get C plus, and this Cl minus is withdrawn by AlCl3, and this is the electrophile which is attacked by benzene ring, and you get benzaldehyde. The so-called Gatterman-Koch reaction. Gatterman-Koch reaction. Benzene converted to benzaldehyde. What is the reagent? Exactly. CO with the HCl. CO with the HCl with a Lewis acid. Fine. And there is one more reaction like Gatterman-Koch reaction. Benzene converted to benzaldehyde by using HCN by using HCN and a Lewis acid, we are converting benzene to benzaldehyde. That is another reaction, that is Gatterman aldehyde synthesis. Gatterman aldehyde synthesis using HCN. Not in the syllabus, I am just telling you as a point of related information. So, Gatterman-Koch reaction we have in the syllabus, benzene converted to benzaldehyde using carbon monoxide and HCl. One more reaction, Gatterman aldehyde synthesis, benzene converted to benzaldehyde using HCl and Lewis acids. Okay, that is a reaction. So, that is preparation of various aldehydes, preparation of aldehydes. We were referring oxidation of alcohols, normal oxidation, then passing alcohol vapors passing through heated copper or silver number 2, then ozonolysis reaction, then hydration of alkynes, then Rosenmund reduction, Stephens reduction, Dibal H, application of Dibal H, and now Etard's reaction. Reaction using in the form of benzylidine diacetate. Exactly right. Then Gatterman-Koch reaction, Gatterman aldehyde synthesis. Next is preparation of ketones. Next is preparation of ketones. That is next. How to prepare ketones? How to prepare ketones? Number 1, from acyl chlorides. From acid chlorides we can produce ketones. What we do is we take a Grignard reagent. A Grignard reagent first treated with cadmium chloride. A Grignard reagent treated with cadmium chloride, we get a dialkyl cadmium. And that dialkyl cadmium interacting with acid chloride, we get a ketone. That is what the reaction. Say for example, we take a Grignard reagent, say for example, we take a Grignard reagent CH3 MgBr, which is treated with CdCl2, cadmium chloride, CdCl2, cadmium chloride, or let it be MgCl, CS3 MgCl plus cadmium chloride. What happens is 2 molecules of this. So, MgCl, 2 chlorine out as 2 MgCl2. 2 2 MgCl2, 2 chlorine here and 2 chlorine, 2 MgCl2 out. And what you get is CH3 with the CD. You get a dialkyl cadmium, CH3, CH3, CD. This is dialkyl cadmium. You get a dimethyl cadmium. Now that interact with the two molecules of acid chloride. See, this is an acid chloride RCOCl, which is interacting with the CD, CH3, CH3, dialkyl cadmium. Now see, this chlorine and this cadmium out as CdCl2, CdCl2, CdCl2 out. And what you get is, this is interacting with the CH3 group. You get CH3, CO, CH3, two molecules, acetone. So I'll repeat. A Grignard reagent is selected, treated with the cadmium chloride, and you get dialkyl cadmium. This is dialkyl cadmium, and that interact with the acid chloride, and you get a ketone like this. Definitely you must have some thought process. Why the reaction is so conducted? Why can't, see how different route we are traveling. Why can't it be straight away a reaction like this? There must be a thought process, and that actually is the building stage of your competitive skill. Why can't it be like this? RCOCl plus R dash MgCl. Why can't there be a direct reaction? MgCl2 out, MgCl2 out, and you get RCOR dash. Why can't it be like this? You see, Grignard reagent taken, treated with the cadmium chloride, you get dialkyl cadmium, and that dialkyl cadmium interact with acid chloride, you get a ketone. See, long procedure. Why can't it be directly? Acid chloride, Grignard reagent, you get a ketone. There must be a thought process. There must be a thought process why this is not adopted. Why this process is not adapted? Rather, this Grignard reagent converted to another organometallic compound, and that interact with acid chloride, you get a ketone. Why don't we do directly with the Grignard reagent? Try to have a thought process and try to get the answer. Definitely these things we are discussing in our classes, and much more. All of you know we are discussing all. Definitely these points might have discussed in the classes. I'm just reminding you as a part of revising. I'm just reminding you, even if you haven't got a picture regarding this, there must be a self-thought process. Sir explained like this. Then why can't it be like this? Learning science, always there must be a thought process. Why can't it be done like this? Okay, try to identify or try to review if already it is learnt. I'm just prompting you to revise, or I'm prompting you to think in such direction. So that's about preparation number 1 for ketone. Number 2, Grignard reagent with the nitrites. Grignard reagent with the nitrites, that is the number 2 procedure. Preparation of ketone from Grignard reagent using nitrite, that is cyanide. An alkyl cyanide or alkane nitrile treated with the Grignard reagent. See, there will be an addition process. Cn polarizes as N minus and C plus. And here it will be breaking lies Mg plus and R dash minus. R dash minus connected to this carbon and N minus connected to Mg. You will get the addition product R, C, R dash, double bond, N, Mg, Br. This is the addition product you get. And then there is hydrolysis. There will be hydrolysis over this region, and you will get a ketone RCOR dash. And this nitrogen will be out as ammonia and MgBr as MgOHBr as usual cyanoria. Clear? So RCN polarizing as N minus C plus, C plus attacked by R dash minus and N minus attack on Mg. You get RC R dash double bond N MgBr, which upon hydrolysis you get RCOR dash. Nitrogen out as ammonia, MgBr, MgOHBr. Perfect. And the last one, FC reaction. FC acylation reaction. FC acylation reaction. Benzene treated with an acid chloride. Benzene treated with an acid chloride, either aliphatic or aromatic with AlCl3, and the reaction perfectly learned during hydrocarbons. So we take benzene or substituted compound treated with CH3COCl, or it may be benzoyl chloride, even no problem. COCl, either this or this, no problem. And it is treated with a Lewis acid like AlCl3, anhydrous condition. It is breaking here as minus and this is plus, and here it is as minus and this is plus. So this minus is withdrawn by AlCl3 and we get the electrophile. This is the electrophile. This in fact is the electrophile attacked by benzene ring. And the result will be acetophenone. In the first case, you get acetophenone, and in the second case you get benzophenone. Benzophenone. So this is acetophenone and this is benzophenone. This is Friedel-Crafts acylation. Friedel-Crafts acylation or benzoylation. Friedel-Crafts reaction. Aromatic electrophilic substitution reaction. Right? And there comes an end of the preparation of ketones. There comes an end of preparation of ketones. Right? Not only ketones, aldehydes and ketones. Aldehydes and ketones. So what are the methods referred? Oxidation of alcohols, catalytic hydrogenation, dehydrogenation of alcohols, right? Then ozonolysis reaction, hydration of alkyne, Rosenmund reduction, Stephan reduction, reduction using diol H, Etard reaction, a similar reaction using acetic anhydride. Then side chain chlorination, three reactions we have seen. Monochlorination, benzyl alcohol, dichlorination, benzaldehyde, trichlorination, benzoic acid. Then Gatterman-Koch reaction, Gatterman aldehyde synthesis, which is not in the textual content. Using dialkyl cadmium, how do you get a ketone? Alkyl cyanides, alkane nitride with the Grignard reagent, how do you get a ketone? And finally, Friedel-Crafts reaction. These are the methods of preparation referred for the preparation of aldehydes and ketones. Try practicing all the reactions. Try practicing. For example, if you take up the second equation here, you see C6H5CH2 twice CD with this. What will be the product? CdCl2 out, CdCl2 out, and what you get is CH3, CO, CH2, C6H5, two molecules, CH3, CO, CH2, C6H5, two molecules. You get this, right? And the name of the, what is the name of the molecule? What is the name of the molecule? 1, 2, 3. 1-phenyl, 1-phenyl, propan, 2 on, 1 phenyl propan, 2 on. That is the product. Is it clear? Is it clear? Fine. So try practice all those questions also. Next is on to physical properties of aldehydes and ketones. Physical properties of aldehydes and ketones. Methanol is a gas at room temperature. Ethanol, volatile liquid. Other aldehydes and ketones are liquid or solid. The boiling point of aldehydes and ketones are higher than hydrocarbons and ethers of comparable molecular mass. So comparing hydrocarbons, ethers, aldehydes and ketones, boiling point is high. But it is less than alcohols. It is less than alcohols. Look at alcohol, molar mass, comparable molar mass. 370 is the boiling point. What about acetone? Next place. Aldehyde, next place. So aldehyde is less than ketone. Ketone, slight upper hand. Same molar mass. So ketone, slight upper hand than aldehyde. And methoxy, ethane, normal butane. So alkane, ether, aldehyde, ketone, alcohol. Very, very important. And ketones can make, aldehydes and ketones can make hydrogen bonding with the water using this oxygen, and polar nature of that CO bond, it is able to make hydrogen bonding with the water. Lower members hence can be miscible. Lower members hence can be miscible, but higher members will be more hydrophobic in nature, right? They dissolve in benzene, ether, methanol, chloroform, etc. Lower aldehydes, sharp, pungent odor, but as the molecular mass increases, the pungent character decreases and becomes more fragrant, and hence used in blending with perfumes and flavoring agents. Try to understand the order. Alkane, ether, aldehyde, alcohol. Clear? I mean boiling point order. What will be the order here? In the increasing order, if I am putting number, lower value. You see aldehyde, alcohol, ether, alkane. So this is number 1, this is number 2, this is number 3, and this will be number 4. It is 1, 2, 3, 4 order. 4 is alcohol maximum, then aldehyde, then ether, then alkane. Order of boiling point. Okay, simple points. Yes. Now on to chemical reactions. Of aldehydes and ketones. One of the most characteristic chemical reaction of aldehydes and ketones are nucleophilic addition reactions. That is the most wanted reactions, most important reactions of aldehydes and ketones. Suppose if you take aldehydes and ketones, the so-called carbonyl compounds. This is carbonyl compound. It is sp2 hybridized and planar. Okay. All of you know this is polarizing as minus and plus. There is C plus and O minus. C plus is electrophilic center. O minus is nucleophilic center. Okay. Tell me which is more reactive. It is C plus or O minus? Which is more reactive? Which will be attacked first? Is it the electrophilic center attacked by a nucleophile or a nucleophilic center attacked by electrophile? Which happens more? The answer is in the rate determining step of the reaction. That is the slowest step of the reaction. Please understand a nucleophile will be attacking over C plus, as C plus is more active. Why C plus is more active? It is electron deficit. C plus is electron deficit, only having 6tet, while O minus having octet. So what will be the scenario? The sp2 planar system now will turn sp3 tetrahedral. C double bond O becomes O minus, and the nucleophile attached here, and here you have 2 free valencies. If it is aldehyde, one position will be H. Okay, so this is what the intermediate we get. Intermediate we get, and the intermediate is sp3 hybridized and tetrahedral. sp3 hybridized and tetrahedral. Okay, and the next step, which is a fast reaction, which is proton capture. H plus will be captured by O minus usually, and what happens is you get like this, O minus usually capture H plus, you get OH and the nucleophile here. And quite interesting feature is, I don't know how many of you may notice, suppose it is X here and Y here, it will be X here and Y here, this carbon turn chiral center. So what kind of product we may be getting? Are we going to get this compound, or are we going to get this compound? Are we going to get hope you understand what I am doing. Hope you understand what I am doing. I am taking the mirror image. I am taking the mirror image. I don't have to tell you if this is dextro, this is levo. If this is plus, this is minus. My question is, suppose it is 2 different units. Definitely it is going to be chiral. Okay. Now if it is chiral, are you going to get this or this? That is a point of discussion. I would say you get both. That means there is a high chance of getting racemic mixture. There is a high chance of getting racemic mixture. How, sir? Because this is planar. This is planar system. Not necessarily the nucleophile is attacking from the top side. Why can't it be attacked from the bottom side? So nucleophile, there is a chance of attacking 50-50 top and bottom. That means there is a chance of getting 50-50 configurations. 50% dextro, 50% levo, not necessarily exactly 50-50. Not necessarily. Always during racemization, we don't get 100% racemic. Of course, we may get, but naturally sometimes slightly upper hand for the certain combinations. So there is the chance of getting racemization, as the nucleophile may undergo 50-50 attack from the top and bottom, or left and right, like that. Okay, so this is what the nucleophilic addition reaction experienced in carbonyl compounds. sp2 planar system attacked by nucleophile first in the rate determining step. You get sp3 intermediate tetrahedral system, and finally you get this. This is applicable only if it is xn by 2 different units. Otherwise, it is not applicable. Now, very important point of discussion, which is more reactive. What is the order of reactivity? Is aldehydes, ketones, everybody having same order of reactivity? Definitely not. What is the order of reactivity towards nucleophilic addition? What is the order of reactivity towards nucleophilic addition? It is HCHO, most reactive, than RCHO, than I don't know how many of you will be able to understand what I mean. RCHO, then ARCHO. ARCHO means benzaldehyde. And then ketones, RCOR, and then I'm just giving you a caricature idea regarding the nature of the molecule and their order of reactivity. This is the order of reactivity. Roughly you can keep in your mind regarding the nucleophilic addition reaction. What I mean, try to understand clearly what I mean. Very simple, very simple. Very simple point. You see, formaldehyde most reactive. Formaldehyde most reactive. Then aliphatic aldehyde. Then what is the difference between this and this? Hope you understand the difference. As the size of the alkyl group increases, due to steric reasons, generally the reactivity drops. So if you have a simple aldehyde and a bigger aldehyde, simple aldehyde will be more reactive generally. And then aromatic acid. So aliphatic aldehyde, formaldehyde, aliphatic other higher aldehydes, then benzaldehyde, then ketones. Now among ketones, this ketone, which is more reactive? Simple ketone will be more reactive. There is a great role for the steric factors, mainly the reactivity governed by steric factors. Steric factors mainly influences the reactivity. If you take a steric and inductive effect, if you are taking formaldehyde, say for example, if you take formaldehyde, you see formaldehyde HCHO, it is polarizing as minus and plus, and this plus will be maximum because hydrogen has no electronic effect, no steric effect. What about RCHO? What about RCHO? This is polarizing as minus and plus. This plus is reduced by plus I effect of R group. Due to the plus I effect of alkyl group, positive center decreases. So this is less electrophilic than this. So nucleophile attack more easily here than this. Right? What about a bigger alkyl group present? If it is like this, CHO, this is polarizing as minus and plus. It's more not about the inductive effect. See, this is having inductive effect, this is also having inductive. Here the point is steric reasons. Since it is a bulky group, there will be a hindrance for the nucleophile to come and attack. So two major points that decides the reactivity of carbonyl compounds. Number one, electronic reason, I effect. Number two, steric reasons. Now, what is happening with the benzaldehyde? Benzaldehyde, due to resonance, the electrophilicity will be decreasing. You look at benzaldehyde. In benzaldehyde, this is polarizing, like just imagine, this is polarizing minus and plus. When this polarizes, immediately this electron will be shifted to this position. Resonance. Due to resonance, the electrophilicity of carbon suppressed. Then what about ketone? RCOR. This is polarizing minus and plus. The plus charge on carbon is reduced by the two-way plus I effect of alkyl group. And of course, when the size increases, steric reasons. So this is very important order. Formaldehyde maximum reactive, than other aldehydes, than bigger aldehydes, than benzaldehyde, than ketone, than bigger group ketones. Right? Fine. Next is various examples of nucleophilic addition reaction. Some important examples of nucleophilic addition reaction.